Welcome to Finite Element Methods. Today I'm inviting Chad Foerster in this guest speaker series where we're learning from industry experts in how finite elements could be a valuable tool, pitfalls to be very aware of, model validation, and other things that we need to keep in mind when using these tools. Today, I have the privilege of having him here, but before we start with that, I want to share a quick video on some of the work that Virgin Orbit has done. Camera, go. High speed camera, go. Ordnance rack, go. 3, 2, 1, fire! What you see there is a flaring separation test. I will now play a new video. Camera, go.
LC, this is LB in control room. We are currently on track for our nominal timeline, and our current drop time as listed in Trillion is 1925 UTC.
Planet controller and flight crew has been boarded the aircraft.
Cosmic Girl, this is Orbit Base. You are go for takeoff.
Copy, go for takeoff.
Altitude 3000.
And Orbit Base, Cosmic Girl is starting the turn to the inbound. Pulling now. Pull.
Pulling.
Release.
Release, release, release.
Release.
EST's ignited.
Confirm Newton 3 engine startup.
Max Alpha achieved.
TBC's in first stage looking good.
We had a pretty awesome view up here.
Max Q Alpha achieved.
Stage 1 burn nominal.
Stage set, brake wires broken.
Newton 4 startup complete.
Recovered, and we are now returning to base.
Bearing, brake wires broken.
Launcher 1's in space. Sounds like the blue skies went to black.
This is Radiohead on control. Mauritius has confirmed acquisition. Payload separation confirmed.
I have invited Chad Foerster, who is the Chief Systems Engineer at Virgin Orbit. He was previously the Chief Engineer at Launcher 1 Evolution, Manager of the second stage structures and mechanisms, and at Virgin Galactic, he was a lead mechanical engineer. He has extensive experience in the use of finite elements, actually, in practice, but also understands the practical limitations of these models. He has an education that encompasses a master's degree in structural engineering from UCSD, and a bachelor's degree from Harvard Mudd College. With that said, I would like to have Chad Foerster start discussing some of the things he would like to talk about. And I do have a list of things to talk about. So Chad, you want to introduce yourself further?
Yeah, everyone hear me?
Yep.
Yeah, it's great. Not sure whether that other video what you're going to pull up, it looked like another 747, or maybe it was our bird. That's interesting. So my name is Chad Foerster. I've known Vinay for a long time. I worked with Vinay at Aerospace Corporation prior to coming to Virgin Galactic, which then became Virgin Orbit. So I went there in 2015. I'm coming up on my 6-year anniversary next week. So it's been a long time. And, you know, this talk is a little bit about at least my path, but also about what I've learned, kind of broad knowledge. Obviously, I can't go into some of the nitty gritty details, but I can talk about kind of, broadly, what I've learned across, multiple different places in my career, not only at my current job, but also, even, learning prior to that at Aerospace Corporation and in graduate school. So, I will say just specifically for final modeling, I would say I really didn't get my feet like super dirt or my hands super dirty into it, application wise until Aerospace Corporation. A lot of stuff that I was doing in grad school was more, theoretical and kind of like use case of like simplistic structures and was helpful. But getting into the more complex, models throughout my time in aerospace and then coming to Virgin Galactic and then working on this Launcher One system is really taken that kind of to the next level. So I've come pretty far, at least I'm in mid-career, and Vinay put up these questions right here. And so I wanted to kind of go over them real quick, and then I could dive into the more detail application specific on final modeling. Well, one of the things I like to tell people, and being successful in a career, and at least how I've done it, is I've always been ready to, jump into a new position, even if I'm not entirely ready. And my threshold is pretty low. It's a 50%. So that's a failing grade. And, but I think being willing to fail and also identifying, upfront how that might happen, but also who might support you is an important thing about being, ready and willing to jump into a new position, because there's a certain amount of timing and luck to certain points in your career. So if you have an opportunity and it's on your career path, it might be a little bit to the side, not exactly what you want to do, but it's on the path, but you don't think you're ready. You need another 2 years in your current position, another 5 years, or even another 10 years, really assess, what it means to jump, and if anything, be ready to interview for that position, fully acknowledging that you're not ready. And sometimes you'll get it and sometimes you won't, but at least you'll go through experience and understand what is needed in that position. So that's what I'd say. I've been willing to do that, and that's helped me advance here, at Virgin Galactic and on the way to being Virgin Orbit. And the other thing that's been successful, I think, and this comes from going to Harvey Mudd, and really this is all over higher education, is like being really willing to learn and being really willing to also be, in some cases, the idiot in the room, the person that knows the least, and asking good questions and really asking questions that you are going to do something with the answer with, not just asking questions, asking questions that materially help you understand the system or help you ask that next question to help the team drive down into a failure or something of that, nature. So those are kind of the two key things. And I think the last maybe component of that, the last, third leg of that stool would be really finding something, if you're passionate about aerospace, what are you really passionate about in aerospace? I really have come to understand, I've always loved airplanes. I always loved rockets. I actually like satellites too. I sometimes have a hard time picking which is my favorite, because there are so many cool things that we've done in all of those realms. And what I love about the position I am in right now, or the company, and why I'm engaged and I'm there, and that's what you really want, is you want engagement and enthusiasm, is the meshing of all those things in one system, where we have an aircraft, we have a launch vehicle, we also have satellites, that we're helping payloads get to orbit, and we're working on some other things where we're developing things that be more like satellites, for getting people into more, higher energy orbits down the road, that's past what our two-stage launch vehicle can do. So that's part of it. That's how successful you have to really ground yourself in, being ready to jump, and having enthusiasm and just going for it. So let's see. The next one, how do you know where to go in terms of your career? I really rely heavily on talking to my mentors. Vinay is actually, one of my mentors. I've, stayed in touch with him ever since working with him in, Aerospace Corporation. And I would say, Vinay, the reason that we know each other so well is just because I was placed in your office. So I shared an office with Vinay for a while. And so you really have to look for opportunities, that are in front of you, and look how those, align to your career path. And don't get caught up about, getting to that next milestone or finishing that next lap. Focus on the steps in front of you. And each step forward, you can probably identify something local, surroundings that might help you, reach your long-term milestone. And I would say, one of those things is actually my relationship with Danae. And so looking for opportunities that are close by you as you're stepping along on your path will help you better define your path and reach your goals, your big goals that seem impossible. And my goals, I really, I think this is kind of, it's a little corny, but it's true. I was a kid in middle school when the whole single stage to orbit stuff was being worked on with the Venture Star at a Lockheed, and that program was eventually canceled. But I just thought that stuff was so cool, and the space shuttle was it was cool, and it was operating, and they had gone through some issues, but I just thought that, like, building a space plane like that's probably the coolest thing you can do. And I really decided that early, and I wanted to do something that would get me there. And there were a couple different paths. It could be flying on a space plane, or working on a space plane, or designing a space plane. And so I ended up doing kind of the path where I was designing through the engineering path, but you could also do, being a pilot, being able to operate those, or going into, something else, which is more, operations and, supporting big fleets, of airplanes. That could be another path to eventually getting to a place where you might be able to support a space plane in the future. And so though that was exciting to me. So I think kind of like really truly identifying your spark and why you're doing what you're doing right now, because you're going through a lot, doing classes and all that stuff, and keeping that, eye on the prize is important. That's your purpose. And that's helped me. And why are aerospace applications so exciting? I think it's exciting because it's stuff that, like, it's almost like we shouldn't be doing it. It's so complex, and there's such a human element to it, in terms of a little human mistake, can have pretty drastic consequences. Know how good you design the system. Like, for instance, the Vega rocket, some of you guys might have known, it just had a successful flight. I believe it was yesterday, coming back from a unsuccessful flight where they swapped two connectors. And so they basically had, their thrust vectoring control was backwards on the upper stage engine, and the whole thing just kind of like flipped and, tumbled, and bam, you don't make orbit. That's something why, like, humans are, it's incredibly difficult to have humans in the loop sometimes, but it's also incredibly important. And because, like, humans can make decisions still in very tough scenarios, and analyze and just go for it, and do amazing things with these complex machines. And so aerospace applications are the future. You're constantly working on the future, and that's really cool to me. And that keeps me involved and excited, and looking and being excited for other people in the industry as well, because if we all succeed, I succeed, and if I succeed, everybody else succeeds. That's kind of how it is. It's a small community, but it's also very competitive, and it's just very, future forward looking.
Chad, those are excellent points. And the reason I showed those videos at the beginning is because to succeed, you have to try. And a lot of organizations put a lot of effort into achieving the dreams of whatever goals they have. And we could see in the previous video how there's two videos, one where there's a nice fairing separation test, And I saw you in a video, and I'm pretty sure you're excited when that separation event occurred correctly in the test. And secondly, the successful launch in January 2021. So those are really exciting milestones that I'm pretty sure get you excited, right?
Yeah, they do. And we had an unsuccessful, or I would say partially successful demo flight last May in 2020. Just after COVID hit, we had to figure out how to do it and operate with COVID. And then we got that flight off, and then we only stayed lit on the first stage engine for, around 10 seconds. We got a ton of data though, and we burnt down a ton of risk. So, it still was, a celebration in that we got something done that people didn't think we could do, right? When I came in 6 years ago, I came to an open house. There were 6,000 people they were going to hire. There's only less than 50 people at the company working on this project. And they had, a concept. They didn't have an airplane yet. They hadn't finalized, they haven't gone through, a preliminary design yet. So it's just, you had this kind of dream. And as we went along, we incrementally burnt down the risk and bit off the elephant and chewed it. And some chews took longer than other chews. And sometimes we had to spit it out and take another bite, and try to digest that. And it's really, that is kind of the life cycle of this. And you've seen that at other big aerospace companies. SpaceX went through their own growing pains at various portions in their life, and they're going through their own right now with Starship. But you have to try, and we've been trying, and that has yielded this successful flight on the second flight. And it's a class of vehicle, an orbital class liquid air launch vehicle that's never been done before. We've done suborbital liquid air launch, metallic. This is all composite liquid air launch orbital class. And it's from a platform, a 747, that's not, out of print, so to say. It's still flying around the world. We got freighters all over the place. And you have something like Pegasus, which I give them a lot of credit. Pegasus was the, orbital class, solid. It's totally different animal, in terms of price, in terms of flexibility, and in terms of the carrier aircraft. They have an L-11011. Lockheed, if everybody ever remembers, Lockheed used to make commercial aircraft. that was a long time ago. There are not many of those left, but there are a ton of 747s flying around, and there will be for decades. So it's just it's really cool to see that kind of like come to fruition. And now in my career here, I've been working on Launcher One Evolution the past 2.5 years, which is basically the near term kind of year to 3 year out upgrades. And I've kind of finished that and handed off the team to execute on it. And I'm going to like being basically a super user of the system as chief systems engineer. And that's super exciting to me, because now that we have this system built, we can think about what are all the things that we can do with it. How can we go to Mars with it? How can we go to the moon? How can we, put stuff, in LEO or MEO or GEO, those type of things. And that's really fun for me.
Yeah, that's very exciting. And one of the most exciting tests that you can have is a rocket engine test. I'm going to play a video of that here.
Yeah, this is our Newton 3 engine. This is up in Mojave. And this is a pretty old test, actually, 2018 test. If you guys looked on LinkedIn lately, we're actually doing some pressure fed testing of the same engine, but an upgraded version at Stennis too. So, testing is awesome. And up in Mojave, we have, testing for propulsion and structures and operations. So it's really kind of an all-purpose area that we use. And what has always happened with the U.S. space program, there's a lot of interesting assets and test stands up there in the high desert, over by Edwards, and over in Mojave, there's a lot of commercial, space launch companies that have operated in Mojave out by the airport, in the desert area of the airport over the years, or over the decades, really. It's been a really interesting area for space development.
Yeah, so Chad, a lot of these systems are very complex in terms of the thermal environments, the fluid mechanics environments. The structural aspects are getting really pushed to the limit due to the temperature environments. Finite elements does play a major role in a lot of these designs in terms of validation, right?
Yeah, I mean, absolutely. I would say, some of these designs are not possible without finite modeling, or they are, but you would have to have a lot more iterations to get it right. And so what I see as finite modeling, and I always think in threes. I apologize for that, but I'm a simple person, and I like to think of the three best things of everything. Finite modeling allows you to optimize quickly. That's one. It allows you to build complex structural or thermostructural systems, right? That could be an engine, that could be a propellant tank, that could be a fuselage of an aircraft, that could be a bus of a spacecraft. All have their own interesting thermal, mechanical boundary conditions and issues, and man, it's just cool to optimize that. And then finite element modeling, it's not just about optimization, it allows you to make decisions. And so it's a tool to make decisions about what you're going to do, what you're going to try next, because it really comes down to testing like this. Testing is where the rubber meets the road, right? Everything else is just paper. It's homework, in class for Vinay, or it's, a paper study in grad school, or, a paper study at Aerospace Corporation. It's really like the end result. The thing that's, super exciting is putting that hardware on and seeing it operate, and really seeing how your model, fits with the operating condition, and taking it to the extreme edges and seeing where your model diverges from reality, if it does. And, whether you have, extra pocket margin somewhere in the system that you can identify and harvest, maybe, or not harvest, and keep it there for, the future.
I did like the word harvest. It's a good word.
Well, I've always wanted to be a farmer, Renee. So, why not? You can go around and harvest, and think of it as engineering. It's like you're an artist and you're a farmer, and you're like a politician. You gotta, because there's a big social aspect of it, especially on these aerospace systems, because it's such a kind of like a complex thing. You really need a lot of complex minds, a lot of complex people's minds thinking about the same problems that you're thinking about, so that you make sure you uncover all of the nooks and crannies.
Yeah, and so with that said, do you have a personal story, without going into too much detail, on how you found finite element to be valuable in the design process? And a lot of times there's two approaches to designing systems. One is a shotgun approach, where you kind of have an idea how everything can come together. Another approach is to put some time ahead of that and kind of go through that analysis that could help you get there. And so, do you have a story where you could share on how that was helpful in the design process?
Yeah, I'm trying to think of a good one. I would say one of the things that's really cool about finite modeling, and this is kind of the decisions, is using it to make key decisions about architectural aspects of a structure that are like localized at interfaces. So with a structure, you might know the shape, like the outer mold line of a car, and or an outer mold line of a plane. and then you want to go in and you're like, what type of interface, should I do, to connect the wing to the wing box? What is a spar layout or something like that? I really think those interface models, and you can do it even in a composite, right? You can go in, you can model a composite joint, right? Like a composite ramp, or a bolted composite connection, or a bonded composite connection. Those are really interesting models because it really tells you a lot, about the capability of the bigger model that you might build next, but it allows you to make a decision about what you might build in tandem with building that bigger model and building the test stand to test that build, and fabricating that bigger structure while you're doing all the detailed final modeling. But it allows you to kind of like parallel process the development by making key decisions on interfaces. So I would say that that's kind of the biggest thing. I would say like a core ramp is it's one I've used many, many times, and that breakout model is invaluable to making decisions.
That's great, Chad. And as you've used these tools, or not recently, but when you used to do some modeling, did you ever make a mistake in the finite model, and how you found that error? I know I have made a lot of mistakes using these models, but how did you? I mean, these are black boxes basically. Could you comment on that a little bit?
Yeah, so I think in general, you just general advice, you're going to make mistakes. You're going to make them at various points in your model development, maybe in the very beginning. So you're rapidly iterating, you're like, oh, that's a stupid mistake, or maybe that was a mistake that I didn't see, but I recovered from it. You're going to make them, and you're going to be in a review, and you're maybe make them, and you're going to be trying to operate something. And you're like, oh man, that's actually wrong. Like, so you need to bring it forward and say like, hey, this needs to be fixed, or this needs to be, we need to acknowledge there's lower margin or negative margin here for this specific scenario, or we need to completely redesign this, right? Because it's not gonna work. We can't thread the needle no matter what. So they're just upfront acknowledge that that's going to happen. The other thing that you want to acknowledge as a final model user is really the depth of your study or background in it, and time on the water and background. Like I remember coming out of Harvey Mudd in way back when, in 2005, and my only really final modeling experience was using Algor. I don't even know if Algor is around anymore, but it was some free final modeling program. We did some stress, profiles in a hole in a plate, for a materials class, and that was kind of the extent of it. We didn't really do any dynamic modeling, some modal analysis or anything, and so a lot of my experience then came with working in industry at Honeywell and seeing people do it for turbochargers, and then going into grad school and getting the mathematical background and really appreciating what it is. and it's a numerical method, and it allows you to to do that, what I said before, it actually make decisions, allows you to optimize, and that's really what it is. But it's not the end all be all. It allows you to do these complex systems, so you have to watch your back and help other people watch your back constantly. And I've made mistakes on material properties, fat figuring is 0, and then chasing my tail and losing 2 or 3 days on an analysis. And I would say in those situations, if you feel like you're chasing your tail and sometimes it's a gut feeling, step back, try to do a hand calculation for what you're doing. Something simple. Go back to your mechanics and materials and just like, does this make sense? If something is this thick and I'm putting this much force on it, or this much pressure, and it's at this temperature, like, or should it be deflecting this much? Does that make sense, right? Because you can visualize. A really powerful tool is the visualization pre and post in final modeling tools, right? The meat is in the background, running the code, but the pre and post helps you internalize and make decisions on what to do with your model next. And so you really will make mistakes. So I would say for everyone, acknowledge where you're at, have your checklist that you follow each time religiously, and make sure you do that. And I would say buddy programming is always beneficial. Having someone look over your shoulder and do a cross check of the model and say, did you check this helps a ton. I've worked with a ton of final modelers that are better than me. I found mistakes, and likewise I've worked with final modelers that are I found mistakes in their code. I've worked with final modelers that are not as good as me, and they find mistakes in what I'm doing. They catch it. So the peer review is the kind of last thing. And that's when that really peer review is really checking the final product. But what I want to say is a peer review extends probably even before that to quick pings and checking these and this and this. And did you follow all of your checklist? Are you sure your material properties are right? Did you use the latest rev? Are you sure you checked a certain box so that you're doing an elastic plastic analysis and it's not just elastic, something like that, right? There's so many hidden things in that, what Vinay said, black box. You have to be extremely careful about what you're doing. And the simpler your model is, the better. That usually is the case, right? Complex models are just, it creates a place for things to hide.
Yeah, so those are great pieces of advice, and I think you covered, the value of peer review. And now, what I'd like to ask you is, a lot of people do finite elements, and so, what is the point of doing any finite elements if you can test everything? What is the point of that?
Testing is expensive. You can't get around it. Even if you're testing some small little widget, you might end up testing it, 1,000 times, because you don't have confidence in what it can actually do. So, final modeling is like I said, a tool, to get into testing. It's also a tool to make sure that you're doing the right testing. You can estimate loads. You can build a test stand to apply those estimated loads, right? Because you can hand calc all this stuff on an Excel spreadsheet. And you can say, this is the moment, and this is the shear, this is the temperature, and I think I'm going to have, this load case here at this event, this load case here. But, really, you're going to want to build for these complex aerospace systems a Craig Bampton model, or like a couple, doesn't have to be a reduction of the model, but a couple loads analysis model. Couple loads analysis is that final model with all the different boundary conditions, running through transients and really coming up with kind of the max loads, that drive the design of your structure, because your structure is going to be designed for probably a specific load case or maybe two, and then it's going to be covering all of the other load cases. And so the final modeling helps you kind of verify that and then make sure you have coverage on the test. So testing is expensive, so you don't want to repeat it a bunch. Testing's, expensive, so you don't want to do it if you don't have to, right? If you have super high margins of safety, why do a test, right? It also means you probably can optimize your structure, but maybe you don't need to optimize it. Maybe the application is some consumer good and you're good to go, right? You're meeting your fundamental requirements, and then you're on weight and you can ship it and sell it, go for it. But for the complex aerospace systems, it's really neat. You need it. And the testing is also super important because it helps you validate your model. So then your model then becomes even more powerful. It becomes able to use in what if scenarios, and you can predict kind of the true boundaries of your design, and potentially, open up operating areas and get more performance or get more flexibility, or even, optimize and get weight and or reduce cost, by reducing the complexity of a structure. That all becomes possible with the FEM. The testing, you can do that, but you have to really dig deep and super optimize the test layout, I don't know if anyone's ever done strain gauging, but it's pretty laborious. And if you want a good test, you're going to have a bunch of strain gauges on there. And you're probably gonna have other gauges too for measuring position, you know, and you might even have some little speckle patterns and look at, you know, doing kind of video deflection monitoring, you know, fancy stuff like that. It gets pretty busy pretty quickly. And so analyzing also is the same thing. You can't analyze yourself out of everything unless you have like really high margins, but then you're probably designing something that can't do some crazy thing that you want it to do. Because all these aerospace systems, right, they're high performance, right? It's an F1 race car. And you know, F1 race cars get beat up and they get essentially rebuilt after each race. And a lot of these aerospace systems, you know, they're like, the planes are amazing. Like, planes are amazing. The amount of engineering that goes into those and the operating lifetime, especially with the old school planes that can kind of just keep on living into almost, it seems, infinity, like a B-52. That's just amazing, right? But like for rockets and stuff, and you have something that's very short life cycle. It's like a drag car that you throw away, and it serves a very specific purpose. And you really want to put all of your effort into making, you know, as much mass go to that satellite as possible, because that's your asset that's going to operate for decades, potentially. So it's you know, that's kind of why you analyze. It's you have to do both, and you will see that in a lot of standards, you know, that Vinay's been a part of writing as well, you know, where you want to test like you fly. And you also, you know, want to have a good analysis that supports your testing and would also support other things down the road, like non-conformances or, you know, increasing the bounds of certain things. And then TLF is test like you fly. That's the last thing. What is TLF? Test like you fly. And you really want to make sure your boundary conditions are as flight-like as possible. And you know, that would be you know, the stiffness of your interface structures for the test stand. That could be thermal, you know, but you want to make sure you're covered for your key kind of driving shear and moments, you know, which is just, you know, free body diagram. Make sure you're covered.
So let's walk through some hypothetical scenarios. And we're going to play a little bit of a manager structural analyst. I'm the structural analyst and you're my manager. And you, Chad, told me to analyze this particular bracket. And day one goes by and I haven't started. I'm still staring at the model. The CAD model has all kinds of fillets, has all kinds of holes, small holes, big holes, has complicated geometry that is really confusing me and I don't know where to start. And this scenario does not apply to me alone. This happens to thousands of finite element analysts. Could you tell us what can you do to get out of that funk? That situation where you're getting stuck, looking at a model, a CAD model, and you don't know how to proceed.
And that's, at least, I just want to be clear, that's not necessarily, in my mind, analysis paralysis, but is that what you're getting at, Vinay, in this first question? Or you're trying to just give me a primer to start off?
It's kind of like an intro to that. But my situation in this case is I'm doing nothing. I'm paralyzed. I'm scared about doing any modeling. And I've seen a lot of analysts not even move a finger because they don't know where to start. It looks so complicated. They don't even know where to start. And so you have a lot of days going by without nothing happening. I've seen that a lot.
Yeah, so in those situations, I break down into kind of like, what computing resources do I have available to me? One, because sometimes you can throw kind of a big monster at a supercomputer or a cluster and get a result that's interesting, and you can do that quickly. Even you know, with like a super fine solid mesh. And I did that at Aerospace quite a bit sometimes to just kind of see, you know, what would happen. And then on the side, I would look at trying to reduce the model, and I would go attack it from both ends, right? Because that's like the brute force method, right? With solid elements and, you know, refined mesh and really tackling all those fillets. You might create something that takes an hour to run, but you just go let it run on the side, right? I mean, that's I know that's energy. It's not free per se, but it is working in parallel to you. The next one is going the other way. So bounding the problem. Go over here and tell me what is the most simplistic thing you can think you can represent this with. You know, if it's a bracket with all these holes and fillets and all that stuff, and I'm like, can we just do a plate model with no holes and no fillets and just connect a bunch of shell elements together and just see what happens, right? And so if I have those two things kind of like working on, you know, I throw the thing at the wall, the solid element. I work on my maybe shell model, which is maybe a reduction. Sometimes shell models are not possible for certain things. So if it's like some complex like gear housing, right, on an actuator, and you're just like, oh my gosh, you know, like I don't even think it's worthwhile me doing a shell element, then you kind of take a step back and try to bound it another place. And maybe it's a solid element mesh, but it's just with defeatured areas so that you can only have, you know, a couple elements through the thickness, you know, not 20, but like maybe 3, right? And then look at whether you can use certain types of elements to kind of make your solution better by using less elements. So there's like certain elements within Abacus, for instance, that are pretty useful because they have extra shape functions in them, you know, that are different than like a normal hexahedral element. And they give pretty good results, but also the computational increase is not that much. So like those are the two things that I look at. And at the same time, I'm in the middle here. So I've created my kind of boundary conditions, so to speak. I'm in the middle. I'm saying like, what are we going to do with this information? It's exactly what I said before is if you're going to ask a question, really understand what you're going to do with the information or the answer. So my question is, what is this for? Well, who is my audience? Is this to make a decision on a research project? Is it to make a decision on a spacecraft that's flying next week? Is it to make a decision on a launch vehicle that might fly in 2 years? What is going on here? And that will allow you to vector to the right side of that path, you know, those two paths that you set up so that you go into the right lane, right? Because if you need a quick analysis, you might want to take a brute force approach, understanding the shortcomings or the benefits, and just like, you know, say that that's what I'm going to do. I'm going to focus on that because I need a really fast solution that I can have pretty good confidence in. You know, if you have something long-term where you want really a nice model, but it's a reduced model, but long-term it would be good for a program, let's say something that's a launch vehicle that's a couple of years out, you're like, I'm going to reuse this model again. I want to put some kind of, you know, meat on the bones to optimize it so that I could make it run quick and snappy, you know, for doing stuff down the road. And then if you're over here and you're like in a research project and you're just trying to make, you know, something that in general will work, you know, maybe a bracket to throw on a test machine, yeah, you might be able to live with a plate model and just go for it, you know, because it can take a little bit more high risk approach. But I don't know, that's kind of my thing, you know, bound the problem. That's great. Bound the problem, yeah, decide why you're doing it and pick your path.
Right, just pick and move. Another thing that's helped me is having that brainstorming session with other engineers to see how they'll approach it, rather than being in a little corner trying to figure out how to move forward.
Yeah, and sometimes it's not even necessary to do a model. I mean, Vinay, I can't talk about details, but we did a model and I was like, we came to the conclusion, we're like, why don't we just like look at the hardware? And we looked at the hardware and it's like, oh, it's not even real. What we're trying to do is not even real. So there's, you know, asking, even if you're the analyst, asking why you're doing it, really understanding it sometimes helps people that are more maybe on the front lines ask themselves and be like, am I really, is that real? You know, did we inspect that right? Is that really a situation that's going on in that hardware? Or is it just maybe a bad technique for inspecting or bad data or maybe a bad process?
Yeah, those are excellent points. And I want to go to the next question, but I'm going to combine 2 and 3 because I see those two play out a lot, especially if you have negative margins. You have negative margins in a location, there's a high stress concentration, near a corner or some sort of bimaterial interface or near a flaw. And those two scenarios I'm combining there are effectively the same. As a stress analyst, you're asked to check a box. Um, but there comes to a point where you have to interpret the results and tell somebody whether action should be taken. And so you will see very often structural analysts or finite element analysts to be faced with these negative margins, and nobody believes them because the stress analysts are known to produce negative margins that never produce a failure. Can you tell us a little bit about how will you handle if you're an analyst with negative margins, whether you should believe the answer or not, and what you should do to move forward?
Yeah, negative margins. I usually I'm a very visual and kind of experiential learner, so I always try to sit down. I don't like looking at the PowerPoint with a screenshot of the negative margin. It doesn't really tell me a lot. It's kind of like, you know, 2D Mario versus like 3D Mario. You can do so much more in 3D Mario, and it's fun. So I usually will get into the post processor, even the pre-processor, both actually. I want to look at the results and how the mesh is responding. And I want to look at the model itself. And I want to see if there's anything weird going on in that area. And so that's what I focus on first with negative margins, is like, look at the elements, you know, if it's maybe like 3 or 4 problem elements, maybe in a feature like Vinay's talking about, you know, expand out by a factor of maybe 5 to 10x, take that model, those elements, and really look at them and be like, is there something weird going on here? Is it not attached? Sometimes you get, you know, nodes that are not attached and it's very imperceptible. And so you get like splits, almost like seams in models, especially shell models. And it's just like an artifact of you getting a model from someone else and not checking it. So it's like a free edge condition inside a model, but maybe you don't have enough displacement or to see it in the post processor. So you think it's some weirdness, but it's really just bad meshing. So or it's just like this disconnected mesh. So sometimes that happens. Sometimes there's a, like, you know, if you're using a model with like a lot of different material properties, you might end up having an area where there's like not the material properties you think they are, or they might be inverted, or maybe they're out of order. Because like I said, there's so many buttons, you have to be careful. And so, you know, I would say version control in models is huge to prevent that, right? Especially if you're handing models back and forth. But those are kind of the things about negative margins. And I'd say I will be honest, I'm a culprit of that. I'm saying that's not real. To be honest, it is real for that model, but doesn't mean that model is right. And so I think having an honest conversation about what are the defeaturing tactics that were used in the model globally and locally at that area of question are very important for informing a decision, because we know through our studies and final modeling that certain features will produce these kind of hot spots, and we have these rules of thumb about like, well, you can kind of ignore that. It just, I don't ever want to ignore it. I want to acknowledge it and find it if it's a mistake, or I want to acknowledge it and say, hey, this is the way it is because we're doing this on purpose. This is how we're modeling it. We maybe have done a breakout model of that area and done a finer mesh or a solid mesh and saying like, this is the real situation going on here, but this is what the global model that I use to assess the entire structure is saying. This is the delta, and this makes it okay. So so like, is the model good?
I think we lost you.
Sorry, I accidentally hit the thing. What was the last thing I said?
We were talking about breakup models and truly trying to understand whether that stress concentration or hotspot has any physical meaning.
Yeah, so it's really all being on the same page. This is up and down, right? Down to the analyst, up to even the CEO. You know, the CEO could be in this meeting with you and be like, hey, can we fly this thing tomorrow? And you're like, oh my gosh, I've never analyzed this case before. I'm putting this in my model now. I built this model and I'm getting this hot zone and I really don't know why. And so you really want to all be on the same page up and down the board. Is your model truly right? So have you done that deep dive and really looked at the pre and post? Both are super important, super important. Go down and look at the integration points on the elements in the post processor, see what's going on. You know, see how it's visualizing your results. Maybe it's doing something funky and doing node averaging or something that you don't even know what's doing, right? And it's showing you something that's not real. And really the integration point is what you want to look at sometimes. And then, you know, being really, truly upfront and acknowledging the defeaturing that you have done. Because it's usually there's some level of defeaturing. Sometimes it's extreme, sometimes it's not. And that will help you, you know, explain what the situation is. Like using an RBE2, we all know like, oh, RBE2s, like there's, you know, they're dangerous, but they're also super useful. So just be careful. Stuff like that.
Right? Yeah, and the other approach on Chad is potentially do a subcomponent level test of the area of concern. That's very cheap test, not expensive. And see if
absolutely.
Right.
Yep. That's like that breakout model, and it's the test analog of that breakout model. And, you know, that could be an interface test. Like it could go down to like what, you know, we did some work at Aerospace on composite core ramps, and we published that data, you know, in AIAA, and that's an interface test, right? So that's a breakout model with a core component that helps you make good decisions on a large structure.
Right. And the final question I have for you, Chad, and I appreciate your time from your busy schedule, is the input conditions. A lot of engineers are given loads and temperatures and boundary conditions, and they have never seen the hardware, and they just take all that data and put it to the model, run it blindly, and they get an answer. But I've found many times where the input conditions don't make sense because the other areas of expertise thought you need one thing, but they give you another thing. How important is to make sure that that communication in the finite element process entail involving other areas of expertise to make sure that you've included everything that should be included and is correct in the first place?
Yeah, I mean, that's like this interesting component of FEM analysis that really you need almost like a systems engineering hat perspective to it, right? You might be a mechanical engineer, that's how you're trained, you know, or maybe you're an aerospace engineer that kind of dived into structural analysis and that's where you've been your whole career. You really want to think like a systems engineer when you're given these conditions. The reason is like sometimes you're given the whole enchilada, right? Like Benet said, it's coming at you from a lot of different directions, a lot of different people that are not necessarily talking with each other. And so you want to kind of synthesize that and be like, okay, do I want to throw all of these things at the structure at the same time, or do I want to kind of pick and choose? And it's not one load case that's fully enveloping, but it's maybe 6 load cases that hit these 6 key operating conditions. So sometimes you can do that without like too much back and forth with those subject matter experts that are producing the loads. But a lot of the time it's more of a collaborative discussion. And sometimes you can find, you know, Easter eggs within each one of those that you can harvest, right? You know, and that allows you to, you know, put your best foot forward for a structure maybe that's already designed and you're making sure that's good to go, or putting your best foot forward in a design review to make sure that your structure is on a path and meeting its mass goals, right? It's not overweight. So it's hugely important. It's really systems engineering. And like Vinay said, you know, sometimes you've never seen the hardware before. And sometimes it's not even possible to see the hardware in certain situations for whatever reason. You know, it could be COVID. COVID's keeping you away from the hardware. Figure out how to get an understanding of the hardware. And people learn through different methods, right? Some people are book learners, some people are experiential or visual, some people are really kind of conversational. So maybe it's talking to that subject matter expert that's been flying this vehicle for a long time and they have the drawings out. There was a guy in structures, Vinay, I don't know if he's still there, Ken Winters, maybe he retired. He was like the Delta 2 guy, right? And you went to him if you had Delta 2 questions, right? So there's a lot of different ways you can kind of learn about what you're doing. And there's an incredible value in doing that. And it allows you to actually push back where you need to on boundary conditions, choose the right, probably, 6 load cases and not the 1 load case. Or if it really is a situation where you can choose 1 load case to cover them all, oh man, that's simple and quick. And you're very efficient, and you'll produce a result that you have confidence in, right? And you might be able to also say like, hey, the structure is actually pretty over designed. It covers everything at once. So it's a very much a kind of a dynamic, social systems engineering, situation when you get input conditions. I know that's really weird with a computer program. Essentially you're running a numerical program with inputs, but those inputs are, garbage in, garbage out, but good stuff in, good stuff out.
So those are excellent points, Chad. And I'll take just one more question. And the question is, can you describe a situation where you made a modeling mistake or where the model failed? I think we already talked about that, but have you seen a situation where everybody puts a good effort into the model and the model did not do what it was supposed to do?
Modeling, the model kind of failed. I would say, trying to pick of a one that I can talk about. I don't know. I did this modeling, which was so simple, and this was like a long time ago, of just a single lap joint, right? Not a double lap joint. And it's a bonded joint model, and trying to optimize the shape of that bonded joint. And really we were trying to use final modeling to optimize the shape, and the modeling just failed to produce. So I guess that it's not necessarily a failure of the model, but like the modeling didn't bear the fruit that we thought it would. I guess that's how the modeling failed. I think in that situation, it was too detailed for what the modeling could do, at least at that time. And you either needed a more specific element to tackle that problem of optimization, or really just go out and test it, just do a bunch of coupons and test it. So I would say in that instance, like I failed in really like pushing for the right thing. And it was just, we kept on doing the modeling and we came to a result that was interesting, but it really didn't, meet the need. It failed to really optimize that design, and really, we should have just cut bait on the modeling and just gone straight for doing coupon testing in that situation, then come back with the coupon testing data and like, how can we create a new maybe element that, simulates, these type of optimized bonded joints. That's the best kind of like vague answer I can give you guys.
That's great. Thank you, Chad, for coming out here and giving us a great talk about the value of finite elements and the things that could go wrong. I appreciate it.